Hello and welcome to another video. In this video we're going to be doing the third problem from Saturday's weekly contest, and it's going to be count subarrays where max element appears at least k times. And in this problem you're given an integer array nums and a positive integer k, and you want to return the number of subarrays where the maximum element of nums appears at least k times in the subarray. Subarray is a contiguous sequence of elements within the array. So let's make this a little bit bigger. There we go. So essentially what we need to find is first we need to find the max element. So in this case it would be 3. And then we need to find the subarrays that contain it at least twice. So we have 1, 3, 2, 3. That's 1. Then we have the whole thing. That's 2. Then we have 3, 2, 3. Then this one. Then this one. And finally this one. And in the second one, the biggest element's 4. And there is no subarray that contains it at least 3 times. So we're going to make this a sub-problem. We're going to solve an easier problem, and then we're going to figure out how to do this. And you're going to learn a lot about subarrays. So let's say we have a problem where, let's actually make it over here. So here we go. So let's say instead of asking for that, we are asked to find all the subarrays that contain A and B. Let's say A is over here, B is over here. And we're just asked to find all the subarrays that contain A and B. And we'll index these as well. So this will be like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the brute force way of doing subarrays is there's one of two ways, but a really common one is for each end index, find all start indices that match criteria, right? So for example, let's say our end index was this one over here. Let's just draw that. Let's say it's right here. Let's actually move this down a bit. Right there. Perfect. Okay, so let's say this is our end index. Essentially what we would do is we would have a bunch of start indices. So let's have this be another color. So we'll say like, okay, what start index can we have? We can have this one. Does this match A and B? No. Does this match it? No. Here, no, 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 no. Then finally this one would be yes. So this would be a subarray. This would be a subarray. This would be a subarray, right? And then you would change the end index and try every single start index for that. So you'd move it over here. And then same thing, you'd say like no, 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 or yes. So notice here for every index, as soon as there is a point where it's yes, like right here for this end index, for this point, this does match the criteria, right? That we have both A and B. That's our criteria, A and B. Notice that once it becomes yes, as we expand it, it's always yes, right? So we can technically find for the end index the smallest subarray that matches that criteria, right? So we can write that down as well. So for given R, find L, or find biggest L where criteria holds, and any L smaller will hold, right? So for example, let's actually move this as well, because I don't need this over here. Let's put it over here. So what I'm saying basically is like, if it holds here, it's going to hold all the way through here. Same thing, if we move this to, like, let's say our given R is 7, it'll be like, no, 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 yes. Right here is the smallest subarray that this criteria holds, right, A and B, and then all of these will hold. So we can easily figure out how many subarrays for a right index given the left, right? So that number will just be left. Or actually, in this case, it will be left plus 1, right? So depending on how you structure it. So in this case, for an index given 7, if we find this left 2, that means there are 3 subarrays that this holds for, right? This one, and this one. And to draw those, so it'd be like this one right here, this one right here, and this one right here. So that's kind of the idea behind this, right? Now, we want to be able to do this really quickly. So we don't want to just be like looping through end indices and then finding a start index for all of them. So let's figure out a way how to do this in O of n time, right, instead of n squared. So what we're actually going to do is we're just going to keep traversing. So let's make this right index. And we're just going to keep traversing until we find both of the items. So we're going to say didn't find it, 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 didn't find it. Now we did. And our left index will start at over here. So let's make this actually another color maybe. So let's say this is like this. So our left index would have started over here and we're not going to move it. Now, once we find an index that works, like here, we know we have both A and B. We can easily figure that out. We can just have some kind of Boolean or something. Then we're going to try to shrink left as much as we can while still holding A and B. So we can move it here, we can move it here, and now we can't shrink it anymore because if we shrink it here, then we won't hold A and B. So we shrink this as much as we can, and now, remember we said that the number of subarrays is just L plus 1. So for this given index 6, the number of subarrays is just 2 plus 1. Then we can move the right, and in this case, we're never going to be able to shrink it, but you'll see how this is relevant to the next problem. So we can move the right. We're going to try to shrink it again. We can't shrink it because we have to hold this A. So basically for all of these, we can't shrink left. So now for 7, we'll also have 3 subarrays, right? So 3 subarrays that end with 7. So we can write that down. So 7 will have 3, 8 will have 3, and 9 will have 3, right? Because now whenever we move the right, we can't really shrink the left because in order to have all of it, it needs to be like this. So total, we will have 12 subarrays here. So our answer is 12. And that's kind of the idea. You just maintain the smallest subarray possible, and then you know anything bigger, anything that the left goes farther on will always be valid. And that's kind of the same idea. So now let's redo this for the actual example that we have. So let's actually, we can probably even copy most of this. So let's try to copy all of this. And let's put it over here. So now instead of A and B, now we'll have some value. So let's say we'll have, let's say our biggest number is, and we only care about the biggest number, right? We don't care about anything else. Let's say our biggest number is 3 and our K is 2. So that's going to be like this, this example over here, except we'll just have a bigger array. So let's just put 3s in some locations. So maybe let's have a 3 over here. Let's probably do it in a different color and make it easier. 3 over here, 3 over here, and maybe like 3 over here. So the idea here is going to be very similar, except we're going to do it one way, and then we're going to show an optimization. So first, what we're going to actually do is we're just going to maintain a hash map because we want to know the location of every single 3. So what we can do is we can just have a hash map of the count of 3s. So we'll have a hash map of like where the first 3 is, where the second 3 is, and where the third 3 is, right? And we can even pre-compute that like right off the bat. So let's say we go through it and we'll say like, okay, we'll get the biggest element, and then the first 3 is at index 2, the second 3 is at index 4, and the third 3 is at index 8. Don't know why I don't have an 8 here. It's kind of weird, but there we go. So we can pre-compute this, right? Now essentially what we're gonna do is we are going to keep going, and we're going to maintain a count of 3s, right? So we're going to maintain a count. So let's see how this works. And we're going to have the same thing, right? So we'll have the same like left and right. So the left will just start over here, and the right will keep moving. So we're going to keep moving until we actually have a count that we care about. So we need a count of 2 or more. So we're going to keep going, keep going, keep going. We could just start at 2 actually, but it doesn't really matter. Like we could technically just start at a count of k if we want to. But technically, you don't have to pre-compute this either. You can just do this on the fly, right? So you can say like, okay, as you go through numbers, store their index. But whatever. That's like personal preference. So here we have a count of 1. So we'll say count equals 1. Now here we have a count of 2. And this is really where we can start doing stuff. So when we get a count of 2, right, now we know that we're going to have something valid because at least like we know for sure that like if we just take the whole thing from 0 to here, that's obviously going to be valid because we have count of 2. But remember, we want to shrink it as much as possible. So if this is location, if this is the second 3 we found, the location we really care about is at location count minus k plus 1, right? Because what we need is we need the location of the first one, because we know that if we're at the second one, in this case, if we need 2, then we need the first one and the second one. Let's say k was like 5, then, or let's say k was 2, and we were at the 4th one, then we would need like the 4th one and the 3rd one. So that's why this is the formula we're going to use to figure out like where this is in our hash map. And so what we can do now is we're say, okay, we're at 2. So then in that case, let's move the left pointer up to where this index is, right? So this is going to be count minus k plus 1. So in this case, this is the first k. And the first k is at index 2, so we can move this up, right? So we can just take this, move it up over here. And now we know like this is the smallest subarray for this given end index where this is valid. And we know our count is 2, so we're good to start recording stuff. So we can say result equals, remember, this is to calculate how many subarrays you have, you take the left index, and we can just figure out how many subarrays, right? So it can be here, here, or here, so it's left index plus 1. So our result here will be 3 for this right index. Now we can keep going. So for this right index, the left will be the same, right? We don't, like, anytime we don't reach a new k, our left index won't move because we need to have 2. So for this right index, we'll also have 3. For this one, we'll have 3. And for this one, we'll have 3. So for these 4, we have 3 each. So that's going to be 3 times 4. So that's going to be 12. So our result is 12. Now we reach a new k. And this is our 3rd one. So which k needs to be the leftmost one? It needs to be the second one, right? Because in order to have 2, we need to have the second one and the 3rd one. So we look, where's the second one located? It's at index 4. So we move the left over here. And now we do the same kind of thing. Like, how many subarrays can we make here? Well, we can make 1, 2, 3, 4, 5. So the same thing, L plus 1. So we're going to add 5 here. So it's 12 plus 5, so 17. And then for this index, because we didn't increase the count, we'll also add 5, right? So this will be 1, 2, 3, 4, 5. So 22. And so that's how you could do this with a hash map, where you basically just record where every single k is, where the first one, second one is, and so on. And anytime you hit a k that's greater than, or anytime you hit a count that's greater than k, then you start moving your left pointer. You don't move your left pointer until then, right? Like, let's say k is 5. You only start moving the left pointer when you actually hit that 5th one. Because then you know, if I hit the 5th one, then my left pointer needs to be on the first one because I need to hold the first through the 5th. And you can use this equation to get this. So that's one way to do it. Now I'm going to show you, and this is going to be O of n time and O of n space, right? Because we have to have this hash map. So it turns out we don't actually need this hash map, because really what we're doing is anytime we find a new value, like, remember our left was over here. Anytime we find a new value and our count is big enough, so our count is 2, which is k. Anytime our count is k, what we really need to do is just move our left pointer to the next value that we have, that is this value, right? So we move it over here. Then when we find the next one, we move it over here. And if we had more 3s in here, so let's say we, like, this was a 3, this was a 3, what would happen is, if you would move this one over here, this would move to the next 3. And then if this moves to the next 3, this moves to the next 3. So you don't really need to have an index. You can just keep moving your left pointer until you find the next 3. And the really nice way we're going to do this is, instead of doing that, the way we're going to calculate this result actually is, for every single index we traverse, we don't even need to care if our count is greater than k. We're always just going to add left, right? So we're always going to do this. Because before we moved left, it's just going to keep adding 0. And then when we actually find something that we care about, we're going to do one slight modification. So like, let's say k equals 2 here, so we need to move this. What we're going to move it to, instead of moving to the actual 3, we're going to move it to the one after, then our math will work out really nicely. So instead of moving it to here, we'll move it to the index right after, which is basically the same thing, but now our math will work the same way. So now for this, now we can just add left because there are 3 arrays. So you could technically move it here and add left plus 1, but it's easier to just say, let's just keep moving it until we pass a 3. So like here, we're going to have, we're going to add 4, which is correct, right? Because there are, or actually no, we're not going to add 4. We're going to add, we are going to add, so instead of adding L plus 1 now, actually, I think I screwed that up a little bit. Instead of adding L plus 1, we're going to add L. So we're going to add 3. Because there are 3 subarrays that actually are viable, which will just be this one, and this one. So that's kind of our idea, is we move it past the 3 that we care about. So over here, once again, we'll do the same thing. We'll say, instead of moving it here, we'll move it right past it, because then we can perfectly add the left number to make our subarrays. So we can add 5 here and so on, because there are 5 subarrays here technically, right? Like 1, 2, 3, 4, 5. And that's kind of the idea. We can just have a sliding window instead of having this dictionary where a sliding window will just, anytime we hit a new biggest number and our count is bigger than k, we'll just shrink the left side to make it the smallest thing possible, and then we'll move it up one index past that to get the actual like number of subarrays. And that's kind of the idea. So you could do it with a hash map, you could do it with a sliding window. Either one is fine, I think. But yeah, the sliding window optimization, once you realize technically all you're doing is once you move this one to the next biggest index, then you only need to move the left one to the next, like, you basically, every time you get a new 3, you need to move the left one to the next 3 and so on. So you don't actually need a hash map, you just need to move it to the next one. All right, and now we can code it up. So we're going to say our biggest num, we're just going to go through the array, get the maximum element. Now we are going to have 3 variables. We're going to have a left, a count, and a result. They're all going to be 0. And we're going to do a sliding window. So we'll do for right and value and enumerate nums. So if value is the biggest num, right? If it's the biggest num, then we're going to increment the count. And we're just going to say if count is greater than k, we're going to keep shrinking the left until we pass another one of those elements, right? So what we need is, if our count is like 3, we're going to keep shrinking the left until we pass whatever the biggest number was. Let's say 3, we'll do that. Right, so while count is greater or equal to k, if nums L equals biggest num, then that means, so really what we want our count is to be less, we want our count to be k minus 1, basically, right? Because the idea is we're going to have, like, let's say k is 2 here, we want this to be here, and we want our left to actually be here, the one right past it, because then we can easily get the subarrays. And the count will be 1 in this window. So we want to basically shrink our count as soon as it's k to be k minus 1. And then we can easily get the subarray. So this will be like 3 subarrays, and then this will be over here, and this will be 5 subarrays, and so on, which is the right number, right? Like here, there's 1, 2, 3, 4, 5. So it just works out better with the math. Okay, so if nums is biggest num, then we're going to decrement the count, and we're just going to keep moving up left until count is k minus 1. Then finally, like I said, at every index, we don't even have to check if we're bigger than k or not, because left will be 0 to start off, so we'll just keep adding 0 to start off. So we can just do this and return the result. And there we go. And so we should have a good sliding window solution. That works, and there you go. And yeah, I think most time complexities are pretty close. So yeah, I think like for these kinds of things, there's not really too much more way you can improve performance. Maybe use like one less variable or something, but it's going to be negligible. So the time here is O of n, and the space here is O of 1, because we were able to do it in place. So hopefully this does clear up for you how to actually get subarrays. And the idea for most of these problems is you can always get all the subarrays with a n squared by just manually checking every start index and every end index. But then you want to figure out, like, how do I actually optimize this? And usually there's like going to be tricks. You just have to kind of figure out the right trick. And for continuous sequences, the first thing to look for is a sliding window solution. So hopefully this is helpful. And if it was, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.